Hello, let's try to go over the exam 2 to see what is going on. As I mentioned in the email for the exam, we have the average. So the average is 63, and we have the highest 90. But obviously, you can see from the exam statistics that quite a few of us are still struggling for the exam 2. So let's try to visit the exam 3 problems to see what is going on. First of all, the exam, I think we are doing much better than the exam 1 in terms of the submission, but still we have a few students, 4 to 5 students, are not following the instruction and just submit the exam paper images instead of PDF files. So that would be a huge trouble in the future for your work. And if you cannot follow the rule, then I don't think that will work too well for you. So try to stick with the notes and requirements for the following exams. So let's take a look at this problem 1. So problem 1 is, as we can see that the problem statement says hydrogen is a carrier to store and deliver energy. However, hydrogen does not typically exist by itself in nature and must be produced from other resources. By the following reaction, so now we obviously we see that we need to deal with that reaction. CO will react with water and produce CO2 and hydrogen. And the good part is all those species would be in the vapor phase in the reaction. And the problem statement says hydrogen is produced by the feed of equimolar mixture of CO and waste and water steam. So we are going to have the same molar ratio of CO and water as the inlet. The feed enters the reactor at 130 degrees C and 1 bar, 100 degrees C and 1 bar. 70% of the water is converted to hydrogen, and the product steam leaves the reactor at 450 degrees C. So the good news is that we have this inlet at 130 degrees C and the outlet at 450 degrees C. So even we are going to have some water left, it's not 100% completion of the reaction. We will have some remaining water, but that remaining water will be in the vapor phase. So we don't need to worry about the condensation involved. If the outlet temperature is below 100 degrees C, then we have one other layer of consideration over there. Excuse me. How much heat shall be transferred to or from the reactor? So we need to look at out of the reaction, we have the inlet of, so if I have some simple analysis, if I have some inlet, if I have this inlet at T1 is 130, P1 is 1 bar, I have the equimolar mixture of CO and water. So we can assume this is 1 mole, this is 1 mole, and the 70% will be for the reaction conversion, and then the outlet will be T2 is 450 degrees C, P2. We did not tell you P2 in the problem statement, but you can see that this is 1 mole of CO, 1 mole of water produce 1 mole of CO2 and 1 mole of hydrogen. So this stoichiometry coefficient change will be 0. So this is why P2 will be the same as P1 is 1 bar, right? And then for the outlet component, we are going to have the remaining CO in the vapor phase. We are going to have water in the vapor phase. We are going to produce CO2 in the vapor phase and hydrogen in the vapor phase. So apparently we are going to have the temperature change. 130 to 450. So there we need to calculate the Cp as a function of temperature and what will be the required heat involved in that process. And also we need to look at this reaction. So we are going to have this heat of reaction. And then in order to calculate that, we need to look at the stoichiometry coefficients for each reactant and products, as well as the heat of formation, so that we can use the standard heat of formation at 298 Kelvin. And then we can calculate what would be the temperature effect on that heat of reaction. So the problem should be straightforward, and I double checked on the homework 4 to make sure that we have been exposed to this type of problem, and we have practiced along those concepts. And the answer is indeed yes. So here is my textbook. So if I look at this homework assignment 4 for the problem 4, which is corresponding to problem to textbook problem, this is 4.34. So there you can see that we need to calculate the ammonia gas into the reactor, and we have some mixture of dry air, and we have a certain conversion, and we need to calculate what would be the temperature or the heat-related calculation. So this is not exactly the same, but quite similar to the exam problem. This is one problem. And then when you look at this problem 5, corresponding to the chapter problem 4.36. So this is the problem of chapter 4. This is the problem of chapter 4. Right. Now, when you look at this problem, this is a gas mixture of methane and steam at atmosphere pressure 500 degrees C, and we're going to have the reaction, and we'll leave this. So initial final always greater than 100 degrees C. We have a certain composition. We need to calculate the heat added to this reactor. I would say this problem is almost identical to our exam problem. And this is the procedures, and you have access to the solution. I do want to mention that we have some students took a screenshot of the homework solution and shared that and explained that the exam problem could be solved more or less the same way. I appreciate that. I think I provided quite generous partial credits for sharing this. But indeed, if you solve your homework for problems by yourself, I think at least you can recall that we have a solution on this same type of problems. So this is a little bit surprising to me that we still have a few students struggling, completely having no idea what the problem 1 is asking about. So this is the problem 5, and move on if you look at the problem 6. So this is let me check. This is actually coming out of the problem 4.43 of chapter 4. So this is one other exercise. Now we have two reactions. Actually, it's a little bit harder than the exam problem, but I've checked the homework 4 statistics. I think most of us are really perfect in the homework grades. So I have a serious puzzle what's going on if you are able to get the homework submission in a perfect way, what's going on for the understanding and for the same type of problem for the exam. So this is the let me see. Okay. This is for the problem 4, and even for problem 6, I believe this is also quite a similar problem. We also need to involve the involve the reactions. Here again, we are having two different reactions, and we need to calculate the flow rate. But indeed, you really need to calculate the heat involved in the exchange, right? So all those quantities, the stoichiometry, and using the provided equations to finish the calculation. So that problem is, let me see, it is a few gas. This is a problem 4.44 of chapter 4. So the bottom line is we have 4 problems, very similar and even harder than the exam problem. And now we have the exam. How do I go back to my screen? Let me see how I can go back to the tabs. I can switch this. Okay. So now if I go back to the problem itself, when you look at the what I have in the solution when I was trying to work on this problem. So like I have, we have the equimolar mixture of CO and water. So I would just go ahead and assume we are going to have 1 mole of CO and 1 mole of water, and then 70% will be converted. So when you write down the reaction involving CO and water, the stoichiometry coefficient would be 1 on 1 will produce 1 molar of CO2 and hydrogen. So if we assume 70% of 1 mole of the initial inlet will be converted, then we are going to produce 0.7 mole of CO2 and hydrogen, right? So after the reaction, we are going to have the following 4 components will be leaving the reactor in the gas phase. So putting together the diagram, this is what we have. This is the T1, P1, the reactor. This is the inlet. We are going to have the reaction. We're going to have the outlet. So now in order to calculate the heat, we need to calculate the 2 types of heat. One is the CP related, right? One is the reaction related. And you can have two different ways of calculating. One is we try to bring the reactor, we try to bring this to 298 Kelvin, right? So this is T1, this is a T reaction. And then after the reaction, we are going to have the reactant, and we bring them back from 298 Kelvin back to T2, 450 degrees C. And then, of course, over there for the reaction, we use the standard state. We are able to have this heat of reaction calculation. This is the one way. The other way is, well, let's try to assume that we are going to have the, like I choose here in the solution. If we are going to have the reactants, so here reactants would be only for CO and water, 1 mole of CO, 1 mole of water. I will bring the reactants firstly from 130 degrees C to 450 degrees C. So that is CO with water. Again, CO with water. Okay. So this is one more and one more. Then here is one more and one more. Then I'm going to carry out the reaction over there. So that would be the reaction of CO water at this 450 degrees C, and I'm going to produce the required compositions over there. So if that is the case, then the heat of reaction, we shall calculate this as heat of reaction should be heat of reaction should be calculated at 450 degrees C. But the convenient part is we just need to evaluate that heat of reaction. We don't need to worry about those reaction products and how we are going to change the temperature from 130 or 298 Kelvin up to the 450 degrees C. So that is the choice I made in the solution. So if we try to take a look at this, the Excel file, then if we try to go over here and try to look at the so you have access to this Excel spreadsheet. Basically, that would be the two equations that we are going to utilize. And you can see that I put together those A, B, C, D coefficients, but pay attention to the unit, right? Whether it's 10 to the -3 or +4, you have to pay attention to those coefficient values. So we have A, B, C, D values we put together, and I try to multiply, I try to do the calculation based on the 1 mole of initial CO and initial water. So here we try to bring the temperature from the T naught 130 degrees C up to 450 degrees C. So if I have those A, B, C, D coefficients, nothing special, we just utilize this equation. Right, I have this A value. A would be the sum of CO and water, very similar for B, C, D for all those coefficients. So that it would be the A, B, C, D coefficients for the mixture of CO and water for the CP values. And I have T final, T initial. So then you just need to use this ICPH, that equation to calculate, right? And then you try to run the conversion. So the values we are going to have will generate this as the Cp dt, and then we just need to multiply by this gas constant value, and we need to do the unit conversion so that we have this as a kilojoule. Okay, so this is the first part. When you try to increase the temperature for the reactants, purely 1 mole of CO, 1 mole of water from 130 degrees C to 450 degrees C. So after that, we need to calculate what would be the reaction, the heat of reaction needed at that temperature. So again, now the temperature for the reaction would be 450. And when you try to look at those coefficients, so here especially I want to point out that when you look at the appendix, we have this would be on the appendix of, let me try to take a look at. So here on the page of 659, we have this heat of formation value for both water liquid and water vapor. And apparently here we need to use this vapor water instead of the liquid water. Some students did not have this correct value for this negative 241.818 value. And then other than that, we need to put together again those A, B, C, D, those CP value coefficients. And for the reaction itself, we need to evaluate the stoichiometry coefficients, whether this is the reactants would have negative coefficients, products would have positive stoichiometry values. So we need to make sure we are happy with those. And then when you put them together, the product of the CP coefficients with respect to their stoichiometry coefficients, then you would have this the reaction, those CP values, right? So this is delta A, delta B, delta C, delta D for the reaction involving the four components. And after that, you simply utilize the listed equation over here. Okay. So we understand what would be the standard heat of formation. That's basically the value you read from the appendix, considering the stoichiometry values. So you add them up for this column H, the four values, then you would receive the heat of reaction at that standard state, 298 Kelvin. And then this one is coming out of the MDCPH, the calculation. Okay, you just put in, make sure you have this delta A value correct. So this is the delta A for the reaction, and you need to think about the use of stoichiometry values. So this is why you have this new A, new I multiplied by the corresponding A, B, C, D coefficients to receive delta A, delta B, delta C, delta D. Then you put them together, you receive this heat due to the temperature increase over there. And then this would be when you add the standard state heat of reaction and this amount of energy due to the temperature change. So that should be your energy value for the reaction. So again, this is 1 mole of CO reacting with 1 mole of water at 450 degrees C, and the reaction yield is 70%. So you are going to have that much of heat involved, and together with the previous calculation where you bring the reactants from 130 to 450 degrees C, then altogether you're going to have that much of heat. Okay, so nothing special. You can double check, click on a specific cell to see what is going on over there for the calculation, and then what would be the final value we are expecting. So for example, this final is in the kilojoule. We already considered the number of mole, using 1 mole as the base. So this will involve the cell of I3 and F25 for the reaction. Okay, so this is the calculation for the first problem. Now let's go back to this iPad again. So the second problem. So the second problem says in exam 1, we had a problem, which is problem 2, to calculate the heat and work along 3 different passes using the same condition. So we are going to use the same condition. Calculate the entropy. This is the entropy change to those 6 steps of the 3 passes. For simplicity, the gas is assumed to be ideal. So this is ideal gas. And we need to calculate, if we are going to manipulate the ideal gas, what would be the entropy change? Okay. So we have the Cp value, and even better, we are going to have the reversible. Okay. So if I have this reversible as the condition, then we understand that ds would be, by the definition, would be small amount of reversible heat over T, right? And here, the problem has made it easy that we are going to have those heat for those processes as the reversible heat. So we don't need to worry too much, or we don't need to design the corresponding reversible paths for the calculation. And the remaining would be exactly the same from the previous solution 1 or the exam 1. We still have 5 more of the ideal gas initial temperature and pressure, and we know this is the final temperature pressure. This is the ideal gas. So that problem, I'm also greatly surprised that the performance was not that great. And when we grade the solution, I think many students are completely lost, have no idea what to start with, and even did not bother to use any of the previous exam 1 solution to help with the calculation over here. I was trying to make it easy, and I thought you have access to the exam 1 solution, so that should take really honestly less than 10-15 minutes to finish this problem. But I think I was too confident in the understanding of the entropy. So let's try to see what is going on. And you can see that in the solution. So this is indeed the problem to test the understanding of the entropy. And then if we try to look at the first pass, and I want to tell you that those I did not start from scratch. I basically just copy and paste. So this is the exam 1 solution you have access to, right? So there we understand that those would be the pass design. This is the first step would be isothermal process. Second would be isobaric, the fixed pressure process, and we have all those Q values, work, so on. So if we try to go back to the isothermal process, and we know that this is the reversible process. So the heat along that process, we can directly utilize the heat calculated for this 1 to 2 this process. This is the reversible process, so we have this Q reversible over there, right? And how about the value of the heat? Well, that is directly from the exam 1. So we don't need to calculate. Oops, I don't see the bar, and how to call this back? struggling with this. Well, I guess I just use this one, and I let you guys to go back and check. So this is a value from exam one. We don't need to do anything extra. Just look up the value and divide this current temperature. Right. This is 25 degrees C. This is the first step is isothermal process, and you have this entropy change from 1 to 2. For the step of 2 to 3, 2 to 3 is isobaric heating. And we know that if this is isobaric, then the heat is the same as delta H, is the same as iPad is very slow today. It's a weekend, it does not want to work, I guess. Delta T. Okay. So this is indeed the equation we are using. So the heat is calculated through the Cp value, Cp dt through the dH. So the small amount of reversible heat would be a small amount of the enthalpy change Cp dt, and we just run the integration from 25 degrees C to 300 degrees C. So this is why if you run the integration, then this entropy change would be Cp log T, and you go from the initial to the final, right? And we know the Cp value. We know this is the 25, this is 300 degrees C. So then you quickly receive that calculation. And then you put together, this is the 5 more. You know what would be the entropy change for pass 1. And the second pass of this process, and you should be able to calculate the overall entropy change. So looking at this second pass, it's almost identical. We just flip the order, right? So now the first is isobaric. We use the CPDT to calculate. And then we are going to have this isothermal heating. But there we know that this is the reversible heat. So we can, again, utilizing the previous calculations from exam 1. So nothing special. We have the two values, and then you just add them up to receive the overall. The third part is more or less the same. So here we try to understand what would be the T1, what would be the T2, what would be the T3, and then you can keep using this calculation, right? If I'm going to have the isobaric, I use this equation. If I use isothermal, then I try to calculate the reversible heat, or if there is no heat involved, like we have for the first process. If PV gamma is constant, then this whole process should be the adiabatic process. I believe this is provided or discussed in the exam 1 solution. So this first part, we don't have any entropy change. So the entropy change is purely coming out of the second pass from the state 2 to state 3. And then we just put them all together, all right? So that is the second one. So really it's nothing special. We just need to recall what is the definition of entropy. You need to recall this is the heat divided by the current temperature, and we need to keep using the reversible heat. And also now when you have the ideal gas, the calculation should be much easier than any other general cases. Now I need to figure out a way to go back to the tab, which is annoying. Mm. Okay, that's very silly of this app. Okay, so this is the second problem. Try to take a look at this third one. The third one is about the residual property calculation. So we have 2 mole of superheated steam is processed to change its state from state A. We have this T1, P1. We know this is T2, P2, and we need to use the steam table and calculate first what is delta H and delta G for the process. This second is instead of the residual property, I try to understand what is the change of the residual property. So nothing special. You need to calculate the 2 residual property at state 1, at state 2, and try to take a look at the difference. Right. So then first of all, if we need to look at this delta H, then this is HA, and I'm going to have HB. So the delta H is nothing special, which is HB minus HA. The delta G would be the Gibbs energy of state B minus Gibbs energy of state A. And then if we need to calculate this G of R, residual property of A or B, then we need to look at the G of the current status, TP, minus G ideal, TP. So we had one lecture problem when we talk about the residual property. We also had the old exam, which is exactly the same problem to this one. I think the old exam problem was more challenging in terms of the calculation. The students were asked to calculate other quantities in addition to the residual Gibbs energy. So still the bottom line here is I don't think the class is paying attention to the available resources or the concepts we have emphasized a few times during the lecture. So again, this problem 3 performance is not as good as I had expected. So let's try to take a look at the solution to see what is the procedure. First of all, recognize the unit, especially in the steam table, we are using this kilojoule per kilogram for those values in the steam table. So you need to run the first step to convert the unit so that you know how many kilogram of steam you are dealing with. Secondly, for the state A, you basically just go ahead and read the steam table. You shall have this entropy and entropy and volume, but you don't have the access to the Gibbs energy. And we'll come back in a minute to see how we are going to utilize the Gibbs energy definition to calculate, which is H minus Ts, right? If you know if you know the entropy, if you know the entropy, the temperature is known, then you should be able to calculate one more extra step. You have this Gibbs energy value. Second one, for the state B, I ask you to run the linear interpolation. We don't have that condition, so we are going to pick up the neighboring two temperatures and run one step of linear interpolation. You're going to have HB and SB. Okay, and then of course over there you're going to have is GB is HB minus TB SB. Okay, so over there you figure out the delta H calculation, you figure out this delta G. As I said, this is a way to calculate delta G. Okay, and then some students forgot to put together the overall. Some students just completely ignore the units and just stop there, so lose some points over here. So this is the part one. It's a test of the units, whether you've noticed or not, and the test of reading steam table. For the second one, then we first of all we understand this is the delta G of residual property, and we try to look at the individual residual property for state B or state A. So for this one, so those would be the property we just calculated from the first part. And then for the ideal gas behavior of that condition, we emphasize that if this is, say, G of R, which is G of Tp minus G ideal of Tp, but we don't have that information from the steam table regarding the entropy or enthalpy of the high temperature, high pressure ideal gas. However, we are able to connect these parts with this real ideal, let's call this as the real, which is the same temperature but a low pressure. And the lowest pressure we have access to would be 1 kPa. Okay, that is the special condition we have out of the steam table. So we are able to figure out the H ID real at that condition, SID real at that condition, and then we need to calculate using the ideal gas behavior based on the true ideal gas, and we try to figure out at this temperature and pressure what would be the quantity for the imaginary ideal gas state. And when you figure that out, then you have the value available to you. So the whole process is nothing special. And again, I want to ask the students to see why you missed this part. Is this because you did not spend time on the lecture example, or you were running out of time to review the other materials, including the lecture summary video, including the old exam? We have very similar problems from the previous years. So then the remaining would be some calculation details, right? We try to understand this is 1 kPa, and we try to figure out what is the value over here. And from steam table, we read the those conditions, and we use linear interpolation one more time, and then we try to put together the calculation. So here I was trying to convince you that when you are moving from the low pressure ideal gas to high pressure ideal gas, the Gibbs energy will change. The pressure change will make a difference to the Gibbs energy. So that is what was going on in order to include this term. And then you may want to pay some attention again over here when you are utilizing the ideal gas equation to calculate the Gibbs energy change. And in the end, you want to put together into this kilojoule uh, per kilogram for the steam table related values. So this is how we are going to receive the uh, calculated value over there. And very similarly, you are going to repeat that step with some patience and calculate the uh, the others the other value, right? So over here, you are going to calculate. This is GB TP. This is GB ideal TP. This is GA TP with its own TP. This is GA ideal TP. So the first one, the third one should be a direct reading from the steam table. The second and the fourth will take some time. To calculate, and along the process, we need to design the ideal gas Gibbs energy calculation, right? And also, you need to acknowledge that the best ideal gas condition we have access from the steam table should be at 1 kPa. So this is all I want to discuss for the exam 2. I hope this will add more details to the existing exam 2 solution.